2.3 Experiments and Variables. An experiment is a situation specially set up to investigate something. Experiments are one of the best ways scientists learn about the physical world. You may do an experiment in your class to investigate how fast a car moves going downhill on a ramp. In the experiment, you set the ramp at different angles. At each angle, you measure how long it takes the car to roll a certain distance. Figure 213. The goal of any experiment is to understand the relationship between the variables. For example, what is the relationship between the speed of the car and the angle of the ramp? To answer the question, you set up the experiment with the ramp attached to different holes in the stand. Each hole is a different angle. You measure all the variables that affect the speed of the car and see how and if they change when the angle is changed. In an ideal experiment, only one variable is changed at a time. Then you can assume any changes you see in other variables were caused by the variable you changed. If you change more than one variable, you can't tell which one caused the changes in the other. The experiment will not still work, you just won't learn much from the results. The variable you change in an experiment is called the experimental variable. This is usually the variable that you have direct control over. Going back to the experiment with the car on a ramp, the angle of the ramp is the experimental variable. The variables that you keep an eye on keep the same are called control variables. If you are changing the angle of the ramp, you want to keep the mass of the car the same each time you roll the car. Mass is a control variable. You also want to keep the distance and position the same. Distance and position are also control variables. If you want to test different angles, then the ramp angle should be the only variable you change. How many marbles are in the picture at the left? There are exactly 7, no more and no less. Unfortunately, measuring most variables in science is not that easy. The reason is that most variables can have values that are not limited to whole numbers. For example, what is the length of the screw under the marbles? Is it 5.1 centimeters, or 5.13, or 5.1342 centimeters? Because you can always add more decimal places, you can never know the exact value of a variable like length. In your experiments with motion, you will use a photogate timer to make measurements to the nearest 0.0001 second. You will notice that they rarely get the exact number 3 times in a row, even if you always do the same thing. This is because any real measurement always contains some error. Error is the difference between a measurement and the unknown exact value of what you are trying to measure. This kind of error does not mean you made a mistake. It is impossible to measure a real variable with 0 error. The best you can do is estimate the error and make it as small as possible. When you make many measurements of the same thing, you will notice that the measurements cluster around an average value. Some measurements are more than the average and some are less. To calculate the average, you add up all the measurements and divide by the total number of measurements you have. For example, the average of times shown in figure 2.14 is 0.1253 seconds. The word accuracy means how close a measurement is to the exact value. The average is usually more accurate than any single measurement. That's because most errors cancel each other out when you take the average. The more measurements you include in the average, the better the errors cancel out. A word of caution: some kinds of error do not cancel when many measurements are measured from data. The point of an experiment is to produce data that allows a scientist like you to come to a conclusion. The conclusion tells whether your idea, the hypothesis, is right or not. You need to know about errors before you can make a conclusion. For example, suppose you think that the pointy car rolls faster down a hill than the blunt cars. The experiment tests cars with different shapes by measuring the time between 2 photogates. Your hypothesis, pointy cars roll faster, predicts that the time between the photogates should be less for the pointy car. One group rolls each car once and records the time in a data table, figure 216. The results show a shorter time for the pointy car. This seems to confirm the hypothesis. Are they right? Have they proved the pointy car goes faster? They have not. They only did one trial, so they don't know how big their error is. Without an error, significance. Earlier, we learned that scientific evidence should be reproducible. This means an experiment gives the same result if you or anyone else does it again the same way. This brings up a key question. How can you tell if results are the same when all measurements contain error? The word same, when applied to real measurements, does not mean what it does in ordinary conversation. When comparing scientific results, same means not significantly different. Significant differences are differences that are much larger than the estimated error in the results. That means that two results are the same unless their differences is much greater than the estimated error. This is important to remember. How can you know the error if we don't know the exact value of the quantity? The way scientists estimate the error is to assume the average is the exact value. The estimated error is roughly the largest difference between the average and a typical measured value. Consider two groups doing identical experiments, Figure 215. Each group does 4 repetitions of the experiment and calculates the average time. Are the two groups' results the same or different? The number line below shows Group 1's data with an estimated error of 0.0004 seconds. The two groups' results are the same because their difference is less than the estimated error. Without an error estimate, they can't tell if the difference in times is significant or not. The same experiment is repeated by a second group. The second group does 5 identical trials for each shaped car. Doing identical trials allows the second group to get an estimated error. The largest difference between the average and the measured value is 0.0007 seconds for the blunt car and 0.0006 for the pointy car. The second group can say that scientifically the data do not show the pointy cars are faster. At the speeds in their experiment, the shape of the car made no significant difference. In fact, the shape only starts to become an important factor if speeds of at least 5 times higher than those you will observe in your investigations. Two results are significantly different only when the difference between them is greater than the error. This is an important consideration because experiments rarely produce exactly the same numbers twice in a row. Numbers that are different in a mathematical sense may not be significantly different in a scientific sense. Pause here and answer these questions.